lecture notes. They're updated on my website. They may or may not be updated on the school website. They will be soon. They're shorter now to reflect what I'll actually be able to cover or cover in lecture. Okay, so continuing with some of the ideas I was talking about in the last two lectures, I want to introduce a little bit of language that I might have slipped into using already, so let me just explain it properly. So when a quantum state is described by a vector, okay, or in other words, when its density matrix is this rank 1 sort of matrix, so as a matrix, it would look like this, right? Zeros everywhere. We call that a pure state. Okay. And then when we have the more general situation that rho has rank larger than 1, the density matrix has rank larger than 1. So if I diagonalize it, maybe it looks something like this, and there's more than one non-zero lambda. Then we call that a mixed state. Okay. So that's one piece of language. There's another that's related, and we're going to see how they're related. Talking about pure states again for a second. But now I'm thinking about two systems, so it's on some tensor product Hilbert space of A and B. If there exists some states psi1, some vector psi1 on A, and then some vector psi2 on B, such that these are equal, then we call that a product state. Okay. And if that's not true, if there's no such vectors, then we say it's an entangled state. Okay, good. So fact is that if this state psi AB is product, then it implies that the reduced density matrix on A is pure. Okay? Another way to say this would be that if this is not product, i.e. if it's, or sorry, if this is not pure, i.e. it's mixed, then this must have been entangled, right? This is just the opposite of that, and this is the opposite of that. Okay, so we can show that, it's easy. And we've done similar calculations already. So if we say that psi AB is product, right? So this is psi AB, and then I'm going to use that it has some expression like this. And if I write this out, that means it's like psi1 on A, tensor psi2 on B, right? And then if I want to form row A, I take this partial trace over B of this expression, psi1. Okay. This partial trace that acts on the B system doesn't see this, it just goes through this, right? I get psi1, and then I get the trace psi2, B. And then, as we've used many times now, this is 1. Okay, so then this is just psi1. And indeed, this is a pure state, right? Okay. Good. So in the first part of this lecture, what I want to do is introduce a tool. It's called the Schmidt decomposition. It's a sort of mathematical tool. which is going to let us better understand entanglement and sort of have a simpler way to work with entangled states. Okay. Okay, so let's think about, for now, a totally general state in my A tensor B Hilbert space. So I just have some psi AB in this Hilbert space. I can pick a basis for the A Hilbert space and a basis for the B Hilbert space. And I can write the state in that basis like this. So I have two indices I and j. I have some matrix Cij, and then I have a vector A, and B, right? So this ranges over the basis for A, and this is the basis for B, and then there's some coefficients. Okay, and there would be some normalization condition on these coefficients that I'm not writing down. Okay, so that's a little bit complicated. There's two indices. What the Schmidt decomposition lets you do is actually write this in a simpler form where you just have one index, and it will highlight for you or reveal for you like the entanglement that is or isn't in this state. It will make apparent if the state is entangled or not. Okay. So the key piece of math that we need to write down the Schmidt decomposition, it's called the singular value decomposition. Okay, so this is a fact from linear algebra. You might have learned it, you might not have. If you haven't, you won't know the proof, but it's a very simple to state thing, so you can just use the thing itself and maybe look up the proof later. So it just says that for any matrix, C, my capital C now, it can be expressed in the following form. So U sigma V, where U and V are unitary, okay, and sigma is, well, it looks like this. So it has entries we can call like sigma 1, 1, sigma 2, 2, 0, 0. Okay. So it's diagonal. It has these numbers, little sigma on the diagonal, and the little sigma are all positive numbers, positive real numbers. Okay, so any matrix can be written in this form. If it's an n by m matrix, then this sigma ends up being an n by m rectangular matrix. For this lecture, just have in mind that this is a square matrix, and then all of these are, if this is n by n, then these are all n by n. Okay, good. So let's use this. We're going to apply it to our general state, right? So I'm going to think about this object with these two indices as a matrix, right? And I'm going to use this to write this out in a special form. So in particular, if I have this two-index object, the singular value decomposition tells me that I can write it as U, I, let's call it K, sigma K, K, V, sorry, sigma K, K, VK, J, where these are the entries in this unitary matrix, and then the little v's are the entries in this unitary matrix, and then the sigmas are my diagonal entries on the sigma. Okay. Okay. So let's take that. We'll put it in here. We get psi AB. I have my sum ij u I k sigma k k v k j I j. Okay. I'm just going to rearrange things. These are all numbers. I can commute them around however I'd like. Oh, sorry. I should say there's a k here, which is capturing that there's this matrix multiplication. Right, there's a sum over k. Naively, there'd be two sums because there's two products here, but it's diagonal, so it reduces to 1. Okay, so I have a sum over k. And I'm going to rearrange things a little bit. I'm going to leave the sum over k out front, my coefficients, sigma k. And then I'm going to have my sum over I, u, I, k, I. And then sum over j, v, k, j, j on B. Okay, so this looks like a quantum state. I is summed over, so this is some object that has one index left, which is the k index. Okay, so I'm going to write this sigma k k. This is some state that I'm calling psi k. And then this is, actually I'm going to call these, let's call them phi. And then this is phi k prime on B. Okay? Okay, so any quantum state can be written in that form where instead of having this matrix with two indices, I just have this sort of one vector of numbers and a sum over one index. Okay. Let's leave that. Okay. So the next thing that we need to know is that there's a little bit more structure hiding here that I haven't written yet, which is that this set of vectors, the phi k on the A Hilbert space, are actually an orthonormal set of vectors. So phi k, phi j on A is delta kj. Okay, and then similarly for the on the B Hilbert space, phi prime j b delta kj. Okay, so I'm going to show you that, and then we'll know what we need to know about Schmidt decomposition. So let's try computing that inner product, say on the A Hilbert space. So I have phi k, phi j, and then I just need to remember the definitions of these things. So phi j came from this sum over some index I, and then what did I say? So it was u I k I. So u I now j I, and then here I have that, but I take the bra, some other index I prime, u I prime k starred from the bra, I prime. Okay. This is just a number. I can move this bra through here and take the inner product there. So naively, I have two sums, I prime and I, but I prime is going to hit I. That's a delta. So I'm just going to have one sum. We'll call it I. And I have u, I, k star. And then u, I, j summed over I. Okay. So in terms of matrices, it looks a little bit like I'm taking some product of like a u star or a u or a u dagger with a u. Maybe that's going to give me some delta. It's a little bit confusing. It's clearer if we kind of sort of just change our notation and think about it in terms of matrices again. So what is this object in terms of matrices? This is like, if you think about the matrix U, and I took the IJ entry, right? That's this thing. And then this, what is that? That's the matrix U. I want to get a star, so I'm going to take the dagger of U, and then I'm going to flip the indices here, right, to account for the transpose. No, so yeah, so this is exactly what's confusing, so it's good you ask. So here, remember this object, this is just a number, right? So when I take the bra, what do I do to all the coefficients in my ket state? I just take the star. I take the complex conjugate. There is no meaning to transpose yet here. So I do really end up with this. But then it turns out that I can write like this sum in terms of a product of U dagger and U. And it's coming from the fact that like I have this sum, and if I wanted to interpret this as a product of matrices, I should have had the indices in the opposite order. So I use a U dagger, I get the indices in the opposite order, and now I have I, and it looks like a matrix product, right? Okay, so yeah, now this sum is accounted for by a matrix product, and then I still need to get this J and K index. Or in other words, I could think of this as like, this is the KJ index of this object, right? Which is also K U dagger U J. Okay. And then we're basically done, right? Because this was a unitary, this goes away, this is the identity. So this is just KJ. Good. So indeed, it's orthonormal. They're orthonormal vectors. Okay. So that's a Schmidt decomposition. Questions about that? Let me pause for a second. Okay. People seem pretty happy. Okay, so now we have this new tool in our toolbox. We're going to use it to learn a little bit more about what I was saying here, about this notion of entangled and product and pure and mixed. So in particular, I said before that if psi AB is product, then rho A was pure. Okay. With the Schmidt decomposition, we can actually see that the opposite is also true. So this is actually if and only if. Okay. So let's do a little calculation to see that that's true. So now I'm going to start with a general, possibly entangled state, or just a totally general quantum state. I'm going to write it like this. So I switched notation here a little bit. My sigma kk became my square root lambda k. The square root's just convenient for something that comes up later. We end up squaring those numbers a lot. And then I replace phi k with just k. Okay. Okay, good. Now let's think about the density matrix on AB. That will be sum over k, square root lambda k, 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 right? That's my ket, and then I need the bra. So let's call it k prime, square root lambda k prime, k prime, k prime. Right, that's just writing this out twice. We'll reorganize this a little bit. It's k prime, square root, lambda k prime, k prime on A, and k prime on B. Okay. Good. Okay, now we'll take the trace to get row A. This is a trace over B. What is it going to do? It's going to act on this thing. It's linear, so the sum comes out, these numbers come out. It acts on B, not A, so this moves through. And you just end up with a trace on here. Right? So maybe let me just actually write that here. So we're going to say row A equals, and then I just get trace over B here. I use cyclicity. This comes around. This becomes K prime K, right? So there's some delta K prime K. So if I go and simplify things, I'll just be left with one sum. I'll have a sum over K, lambda K twice, which is squared, square rooted. That's why I put the square root. So lambda K. And then K, and then there was a K prime, but K prime is K, so it's K again. Okay, so that's very convenient, right? This form for the pure state on AB, when you trace out, immediately gives you the diagonalized version of row A on A, right? So in other words, this is the eigenvector of the row A density matrix, and this is the eigenvector of the row B density matrix. And then they kind of sit together like this in the larger state on AB. Okay, good. So now we can see my claim from here, right? So what does it mean in terms of this expression for rho to be pure, right? For rho to be pure, I'm just supposed to have one state psi, right? So in other words, this is a pure state if there's only one non-zero lambda k, right? Let me write this out. So pure, so rho A pure is if and only if there's only one non-zero lambda k. And then if I look at this expression for the pure state on AB, what does it mean to be entangled, right? It's exactly, if there was one lambda k, then this would just be some, kk, and it would be product. And when there's more than one lambda k, that's exactly when it's entangled, right? So, so psi AB entangled. Okay, and then we're done, right? Okay, good. So we're going to go in the rest of this lecture to apply this to some subject in cryptography, in quantum cryptography, as we've been doing in this course. Before that, though, I want to get you to get a little bit of practice with this, get you comfortable with it. So a little exercise, or an exercise for you to think about right now. I'd like you to tell me which, if any, of these following two states are entangled. So the first one is 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And the second one is 1 over root 3. 0, 0 plus. Okay. So tell me which is entangled. If you do that, then find for me the Schmidt decomposition of these two states. So try and write them in this form. Okay? Take a few minutes, put up your hand, I'll come around. Okay. So let's keep going. Let me say something about that exercise. So let's start with psi1. Okay. So you can notice that like every term is here, right? 0, 0, 0, 1, 1, 0, 1, 1. And that means that if I do this, and I factor everything out, I'm going to get all of those terms, right? And so what is this, right? This is just some state on A, tensored with some state on B. Right? Or it's like plus plus. Okay, so this is not an entangled state. If you did the calculation and you computed row A for that state, then you should have found that it was pure. And then that tells you this, or you can just sort of see it by guessing. Okay, okay, and then the other one, psi2. So psi2 actually is entangled. It's a little bit harder to see the Schmidt decomposition. It's not too bad. So you can notice that, wait, how did I do this? Looks like I wrote it wrong in my notes, so let's see if we can just do it. Okay, I'm actually having a hard time doing it. Okay, so you can check that this is entangled mechanically by computing the reduced density matrix. We could do that. That I can do on the fly. So we're going to get 1/3, and we're going to get, you know, these, well, a lot of terms from all the possible pairs. So like 0, 0 plus 0, 0, 0, 1, and so on. I don't really need to keep all of them. I only need to keep the ones where this number matches this number, because those are going to survive the partial trace, right? So I'm just not even going to write this down, that term down. But 0, 0 with the last, with 1, 0 is going to survive. And then 0, 1 will survive with only itself, 0, 1. And then the last one, 1, 0, will survive with 1, 0, and then 1, 0, and 0, 0. Okay, and then if you take the trace, you're going to get 0, 0, plus 0, 1, plus another 0, 0, plus a 1, 1, plus a 1, 0. Okay, and then if you wrote this as a matrix, you could check that this is not a rank 1 matrix. There's a bunch of terms. Okay, good. Okay, so that's it for the Schmidt decomposition. Now let's get to the cryptography. Okay, so last time we were talking about sending secret messages. This time we're going to talk about a different goal. Okay, we're trying to do something else. And what we're trying to do is something called bit commitment. Okay, so what I want you to imagine is that Alice, we have two players again, Alice and Bob. okay? And what we're going to try and sort of emulate is the following functionality. So we're going to have Alice take a bit, either 0 or 1, that she decides on, and she's going to like put it in a safe, okay, with a lock on it, her locked safe. So she puts her bit inside the locked safe, and then she sends the safe over to Bob, okay. And then you wait for a while. Okay, so some amount of time passes. And then Alice is going to send the key to unlock the safe. At the later time, Bob opens the safe, and he gets back, you know, the bit B that went in. Okay? So what's important here is that once Alice puts her bit in the safe and gives it to Bob, she can't change the value of her bit, right? It's in Bob's safe. Bob is not able to read the bit before Alice sends the key, okay? So that's why we call it bit commitment. Alice is committing to this bit. Bob is finding it out later. Okay. Yeah. Oh. Yeah, so I guess I don't want to dwell on it for too long. I'm just taking this state. I'm forming the density matrix by taking the outer product, psi2, psi2. I'm tracing out B, and I'm looking at the matrix I have left. Okay, and those turn out to be the entries. If I did it right, which maybe I didn't, those turn out to be the entries in the remaining 2x2 matrix. Okay, and then if you want to see that that thing is entangled, you are checking that this thing is rank larger than 1. So it's some 2x2 matrix. You could diagonalize it and see what its rank is. Yeah. That make sense? I skipped a lot of details, but that's the procedure. Yeah. Okay, so this is the functionality that we want. This comes up all over the place in cryptography. It's a basic tool that we use to achieve lots of other things. We want to do it not by using a safe, but just by communicating information, right? So instead of a safe, we want Alice to just send some message that depends on B in some way. Bob's not able to read the message until sometime later when he gets the key, and Bob's able to unlock the message. Okay. Okay, so okay, so a general protocol for doing this, when we're not talking about safes, but we're talking about information, has 2 parts. So there's what we call the commitment phase. Okay. Here, Alice chooses her bit B. She's going to prepare some quantum state, psi, which can depend on B. So there's 2 possible choices of psi, right? For B is 0, she prepares one state. For B is 1, she prepares some other state. I'm going to denote them both like this. B is a variable. This is going to be a state on 3 systems, which I'll call A and B2 and B1. And then she's going to send B1 to Bob. Okay? And then the second part of the protocol is the reveal phase. So here, Alice sends B2. Okay, and then hopefully after Bob gets B2, he's able to figure out what B is, but not before then, right? Okay, so for this, this is a protocol. This is our general form of our protocol, right? And then the things that we want to be true about this protocol are two things. One is that it should be what's called hiding. Okay, so this basically says Bob doesn't learn the bit B early. Okay. How would I express that in terms of density matrices and my states and the objects appearing in my protocol? Do we have an idea? Sorry? Right, so Alice is going to start out. Sorry, so the question was, can you say again what B1 and B2 are? So saying this is a totally general protocol for trying to do bit commitment. Alice prepares some state that depends on her choice of the bit. The state has three parts, A and B2 and B1. B1 is the thing that she sends to Bob initially. So it's kind of playing the role of the safe in this analogy, right? So this safe is like B1. And then later, she's going to reveal the bit by sending the second system B2. Okay, and so that's like the key. Okay, so B1 is like the safe. B2 is like the key. A is some extra stuff that Alice could hang on to that she never sends to Bob. Okay, it won't play a big role. Other questions? Yeah. So yeah, little b is the message, and yeah, it's just some single bit, 0 or 1. Yeah. Okay. Okay, so I want to express this condition mathematically, right? And if I think back to the sort of arguments we were making last time about the one-time pad, the way for us to say that Bob can't learn anything about the bit B early, i.e. from the system B1 alone, would be to say that the density matrix, let's call it psi, on B1 shouldn't depend on the value of little b, right? Whether Alice puts into her safe 0 or 1, the thing that Bob sees initially should just always look the same. So the way we can express that is that we say, the density matrix when you put in little b is 0 should be equal to the density matrix when we put in little b is 1. Okay, now there's a second part here. So remember that in the analogy with the safe, we wanted two things, right? We wanted that Bob couldn't open the safe early, and we also wanted that Alice couldn't change the value of her bit after she's committed, i.e. after she's sent this first message to Bob. So this is a property we call binding. Okay. Okay, let me just write it down. So Alice can't change a little b after the commitment phase. Okay. So we also need to think about how we can express that precisely or mathematically. So here, the condition is that, so there should not exist any choice of unitary acting on A and B2, or sorry, A and B2, such that V A B2 psi 0 A B2 B1 is psi 1 A B2 B1. Okay, so why does this math express this sentence? Does somebody have an idea? Yeah, that's right. So B1 is the stuff that after the commitment phase, right? After the commitment phase, she doesn't have anymore. So she can't do anything to B1. She's going to do a unitary that acts on the remaining stuff, the stuff she still has, and see if she can flip the state from the thing she sent, when she commits to 0 to the thing she sends when she commits to 1. Right? If she can do that, that's bad. It's not binding. Okay. Yeah, we can also notice that if Alice had committed to 1 and then wants to flip to 0, she could apply the dagger of this V, right? And that will flip 1 to 0. Okay. Okay, so I claim that the following theorem is true. Bit commitment is impossible. The laws of quantum mechanics just do not allow you to build a system, to design some protocol that has both of these properties. Okay, so there's some fundamental restriction from quantum mechanics on what you can do in cryptography in this context. Okay, so why is this true? We're going to make use of our new tool, our Schmidt decomposition. So let's start out by writing a general form for this state that that Alice prepares, or the two states that Alice prepares, right? Because B could be 0 or 1. So using the Schmidt decomposition, this looks like this. Okay, so here I've collected the A and B2 systems together. I'm thinking about them as one system. B1 is the other system. And then I'm applying the Schmidt decomposition, right? And I'm really applying it to two different states, the psi 0 and psi 1 states. So I have two different sets of numbers here and two different sets of vectors here. Yeah, go ahead. Yeah. It's like we're interested, like, this is sort of the relevant thing to write down when we're interested in this point in time when Alice has sent B1, but is still holding A B2, right? So this expression is capturing for us the entanglement between Alice and Bob at that point in the protocol. Yeah. Yes, that's where we're focused, yeah. Okay, we're going to use that, and what we're going to use it to show is that that if you satisfy the hiding property, then it implies you do not satisfy the binding property. Okay, so that's where we're going to get. Okay. Okay, so that of course means that you can't have both of them at the same time. Okay, so to do that, first step, we're going to compute the density matrix on B1. Okay, so we're focused on this setting where, or this point in time where Alice has sent B1 to Bob. We want to look at the density matrix on B1. We're going to impose the hiding property, which is that that looks the same in the two cases of B is 0 or B is 1. So if I compute from here that density matrix, so psi B on B1, okay, we did a very similar calculation a moment ago, so I'm going to skip it. But what I will get is some sum over I mu IB, and then psi IB psi IB A B2. Oh, sorry, what am I doing? I want the B1 density matrix. So this is phi and phi. Okay, so that's what you would get by tracing this thing out. And then what we get from the hiding property is that this state should not actually depend on little b. Okay, so in other words, it's telling me that mu 0 I, phi 0 I, phi 0 I should be equal to mu 1 I, phi 1 I, phi 1 I. Okay, is there questions? Is that too fast? Sorry, could you speak up? This? Yeah, so this is the reduced density matrix on B1. Yeah. So I've taken this and I've traced out A, B2. Okay? Is it better if I do that calculation? Or it's okay? Both what, sorry? Yeah, this is ket bra phi. Yeah. Okay, let me write it more clearly. Okay? Yeah. That's right. So to understand what Bob can see, we trace out Alice's systems. And we're left with a reduced density matrix on Bob's system, which at this point is B1. Right? Okay. Okay, so these two expressions need to be equal. You can convince yourself that that does mean that the mu 0 i's are equal to the mu 1 i's, and the phi i's are equal as well. Or in other words, yeah, so these are the same these are the same matrix, and when I diagonalize them, I need to get the same eigenvalues and the same eigenvectors. Okay, so good. So that lets me simplify this expression. So let me define a new symbol, mu I, okay, which is, these are equal, so I'm just like dropping the little b index. Yeah. Yes. Yeah, sorry. Okay, so I'm going to define mu I to be equal to these, which are the same. And I'm going to define phi I, yeah, like this. Okay. And so then my two states on A, B2, B1 look like this. So I can simplify them a little bit. So I have square root mu I. There's no index here now. Psi B I, A, B2, and phi I. Okay, so these are two possible states with different, like there's the two values of B I could put in here, but we're saying they're actually kind of similar in that these numbers are the same and these vectors are the same. Okay. So we're interested in that because the more similar we can make these two expressions in the 0 and 1 commitment cases, the more plausible it seems that Alice is going to be able to cheat and flip the two states into each other, right? Okay, and indeed, at this point, we can see actually that Alice can cheat. The protocol is not binding. And in particular, we can choose the following matrix, or unitary, V, which will be defined this way. Okay, some, call it J, psi 1 J, psi 0 J. This is on A, B2. Okay. So I need to show two things. I need to show that this is actually a unitary, right? And hence a legitimate thing I can do in quantum mechanics. And that this will flip the 0 state into the 1 state and let Alice change her commitment after, change her bit after she's supposed to have committed. Okay? Good, so let me try and do that for you. Okay, so let's first of all show that this thing's actually a unitary. So we have V dagger, AB2V, AB2. I get J, psi 0 J, psi 1 J, and then that's my first matrix, and then the second one looks like let's call it K, psi K with a 1 and a 0. Right? So this is, when it's V, it's 1, 0, and then when I took the dagger here, that flipped and I got 0, 1. Okay. Take the product, I get J, K, psi 0, J, psi 0, K, and then I get this inner product here. psi1 j, psi1 k. Okay, but what is this? This is delta, yeah. And it's delta because I showed earlier that the vectors that appear in the Schmidt decomposition are orthonormal, right? So I'm using orthonormality there. And what is this? Well, this is now sum over j, psi 0 j, psi 0 j. So this is just the identity. Okay, good. So that's part one. It indeed is a unitary. The second step is we need to show that it actually lets Alice cheat. Why is that? Well, we want to do this computation. We want to apply VAB2 to psi 0 AB2, B1, and we want to see that this is equal to psi 1, right? So let's do that. Sum over j, which way does this go? 1, 0, psi 1, psi 0, j, j. Sum, let's call it I. Okay, maybe. Psi 0, I. Okay, and then what's going to happen here, this is going to hit this. It's going to give me a delta ji, again, because of orthonormality. Right? My two sums are going to become one sum over I. I'm left with this vector on AB2. So indeed, it's square root mu I psi 1 AB2 phi I. Okay, which is exactly psi 1 A, B2, B1, right? Okay, so Alice can cheat. Okay, so there's no way in quantum mechanics to do this bit commitment thing. Okay, good, so that's everything I want to say. Yes, I hope the main takeaway is that you know the Schmidt decomposition now. It's super useful. You get some practice with it. You see what it can be used for. And yeah, that will serve you well. Okay, so thanks. Questions?
AB2 space?
Yeah, we didn't have to put any conditions on Alice's density matrix. We just put this hiding condition on Bob's density matrix.
Yeah, but that's in the base of Bob, okay, the density matrix of Bob. But what about the density matrix of Alice? So I understand that we don't know anything about that.
Yeah, we don't know much about that, and we don't need to know much about that.
Oh, yeah.
We didn't have to talk about it to prove this theorem.
Okay, thank you.
Yeah. Yeah. A, yeah. So that's just to make the protocol as general as possible. So a thing that Alice could do is, you know, in this protocol, she could hang on to something even after she sends the reveal, sends the key. And A just accounts for that.
Like an entangled qubit.
Yeah, it could be entangled with B1, B2.
Okay.
Maybe that helps her. It turns out no, because even if we include it, she still can't. So it's just being as general as possible. It turns out not to matter that much, though. It doesn't really help.
Binding means that you cannot hide.
I actually don't know off the top of my head. You could think about it, yeah.
I just wanted to know if this, the conclusion is that in quantum mechanics we can do byte commitment like procedures. Classically, we could.
Well, classically, you should think of the classical scenario as some special case of the quantum scenario, and so this actually proves that classically you can also not do it. Yeah. Yeah.
Yeah. Thank you.
What I wanted to ask is this VAB2 operator that Alice sends after sending the message or the bit.
Alice applies, yeah.
Yeah. The fact that it's an operator that acts both on the A and B2 space, I don't understand why it also affects the space corresponding to the key.
So you should think of B2 as the space that is the key or holds the key. So it's like Alice can act on any degrees of freedom she has along with the key that she's going to send to Bob. And so that's why this V is allowed to act on A and B2.
Okay, thank you.
Maybe you should ask me after. You don't look super happy, so yeah.
I was going to ask what in physical interpretation can we give this, this problem, the fact that it doesn't work? Is it because something with the, I don't know, as soon as Bob opens the box, it's a different state or something like that?
I don't know how to interpret it. I don't think there's an interpretation that's that simple. It's just saying that it's expressing something basic about quantum states, which is just that, I don't know how to say this, once you know Bob's density matrix, so Bob has some density matrix here, psi b b1. Once that's fixed, every state that's consistent with that can be switched into any other state that's consistent with that by acting on the remaining outside degrees of freedom. Yeah, I don't know. It's a bit of a mouthful, but yeah.
Oh yeah, it translates.
Yeah, yeah.
Hello. So this is saying that it's basically impossible to hide perfectly the information, but is there another way in which you could transfer information, not perfectly, but pretty secure?
Yeah, so that's a good question. I imposed here that it's perfectly hiding, and then that implies that it's completely non-binding. In reality, there's some trade-off. I could sacrifice the hiding property a little bit and get some amount of binding property. I haven't made that precise. I haven't given you the tools to make that precise. But it's an interesting question that you could study. In practice, it's not very good, and it's not it doesn't sort of lead to a practical protocol to let things be approximate. Yeah.
Thank you.
Well, to me, this sounds pretty similar to the Heisenberg uncertainty principle. So can you formulate something like that? You have more hiding and you can have less binding, or maybe some analogy, or is that possible?
I'm not sure. I've never studied the approximate bit commitment in detail, so I'm not sure what it looks like. Sometimes, but in general, in quantum information theory, there's often these sort of trade-offs where, yeah, you can measure one thing well or the other thing well, and they trade off, or yeah, you can accomplish one goal, like one goal kind of trades off with another one. It happens a lot. I'm not sure if there's some deep mathematical analogy to Heisenberg's uncertainty principle in particular, but yeah.
Okay, thank you.
Okay, so let's thank Alex again.